welcome to EC Electronics. This is a purely competitive exam based video in which we are going to see some tips to solve the pole Zeroplot based questions. Okay, so in any of the exam connected to electronics, that is competitive exams or your semester exams, you will have to answer the questions from the pole Zeroplot. So this is a topic from control systems. Okay, so you will be asked to find whether the system is stable, whether the system is causal, whether the system is having minimum phase or non-minimum phase. Like these questions, you will be asked to find from the pole Zeroplot, or you will be asked to write the transfer function from the pole Zeroplot. Now I'm going to tell you some tips how to identify the system properties and also transfer function from the pole Zeroplot. Okay, before going into all of these, what is actually a pole Zeroplot? It is a graphical representation of your system's transfer function. You know that the system transfer function is a form of y of z by x of z, or y of s by x of s. That is your output by input. That is called your transfer function. Now, if you represent this transfer function in a graphical format, you can call it as a pole Zeroplot. Okay, so this pole Zeroplot, I'm going to say very basic things. I won't be explaining it elaborate, just the key points which you need to know. Now this pole Zeroplot will be having poles and zeros. Okay, so what is pole, what is zero? Now if you represent your transfer function in the continuous time domain, it will be most of the time in Laplace transform, or in the is a transform for a discrete time system. Okay, so I'm going to take a h of z. So this transfer function, if you represent in a graphical format, as I said earlier, you will get a pole Zeroplot. Now this transfer function is having a numerator and a denominator. Okay, so like this the transfer function will be in general case. Okay, and this numerator, if you equate to 0 and find the factors or roots, you will get zeros. So the zeros is actually the roots of your numerator. Now if you equate the denominator to 0, you will get the poles. Now this poles and zeros has a very major role in saying that whether the system is stable, causal, and also whether it is having minimum phase or non-minimum phase. So majorly all the properties can be determined from the position of these poles and zeros, and this is explained with the help of a pole Zeroplot. So that is a very basic or very summarized definition of a pole Zeroplot. Okay, so I hope this much is clear. Now this pole Zeroplot, as I said earlier, if it is for continuous time signals, that is for CT, continuous time signals, in 90% of the case, you will be taking the Laplace transform. Okay. And if you are defining it for discrete time systems, you know that there are continuous time systems and discrete time systems. So, if it is for continuous time systems, you will be using Laplace transform. If it is for discrete time system, you will be using Z transform. So, this is also another thing you have to know. Now, what all are the major properties you can identify from a pole Zeroplot? Now, let us talk about that. So, this pole Zeroplot, we are going to talk about the properties. That is, what are the properties which the pole Zeroplot help us to find? The first one is stability of the system. We'll talk about all of these in brief. Okay, stability of the system can be found from the pole Zeroplot. Second one is causal system or non-causal system. That is causality property. Causal or non-causal or acausal. Then third one is the phase, which is minimum phase and non-minimum phase. Then fourth one is the region of convergence, or you might have seen this term ROC, or region of convergence. Now this region of convergence is helping us to define the causality and non-causality property. Okay, so these are the terms, or these are the properties which you can figure out from a pole zero plot. Okay, so let us see in brief about each of these. First one is the stability property. So how can you say the system is stable? So if just take a function f of t. This is a function of a system, and the system is said to be stable if this function f of t tends to 0 as time tends to infinity. This is a condition. That is, as time is tending to infinity, when the function of the system is tending to 0, that is, it is going on decaying to 0, then such a system is called stable system. Or if you draw the graph of this system, it will look like this. The time will go on to infinity and the function will decay to 0. I'm just drawing a rough figure. Okay. So it will come to 0. So this is the f of t. So such a system is called a stable system. That is, we say as time passes, everything has to decay or everything has to get stable. Likewise, the system is getting stable as time is tending to infinity. Such a system is called a stable system. Now, what is an unstable system? It is the reverse of it. That is, the system is actually going to infinity as the time is tending to infinity. So, it will be a reverse case. So, it will go to somewhere infinity as a time is going to infinity, means such a system is called a unstable system. Now, this is an unstable system. Okay, I hope the concept is clear. Now, how can we identify the stability property from the pole zero plot? I'm not going into the details of the theory and everything. I'm just telling you, if you are given a pole zero plot, how will you figure out whether the system is stable or not stable? Okay, so I'm just drawing a pole zero plot. In the S domain, there is sigma, there is j omega. Now this axis is called the real axis. This axis is called the imaginary axis. Okay, and another important thing to note is that in pole zero plot, there are poles and zeros. This poles is represented with the into mark like this, and zeros are represented with a small zero circle, small circle. So that is a denotion of representing the poles and zeros. Okay, so this thing also you should know. Now this is a pole zero plot. Now in this pole zero plot, I'm going to talk about the stability property now. In the pole zero plot, if all the poles are on the negative side of this plane, so this is the negative axis, this is the positive axis, or this is the left half of the plane and this is the right half of the plane. If all the poles are lying towards the negative side or the left half of the plane, that is, the poles will be like this. Okay, so if the poles are lying in the left half of the plane or they are negative, the poles are negative, say it is -3, -4 or -1 like this. So if it is like that, then the system is stable. That is, if all the poles are in the negative axis or negative side or in the left half of the pole zero plot, then the system is stable. And if at least one pole is in the right side or the right half of the plane or in the positive axis or the positive side, then it is called a unstable system. Okay, so I hope this concept is clear. So if the poles are in the negative side, then it is called a stable system. Otherwise, it is called a unstable system. So that is all about stability. So if you are given a pole zero plot, now you will be able to find out whether the system is stable or not, right? So you have to look for this INDU, that is your pole. Now, what is causal? What is a causal system? Okay, so a system is said to be causal. I'm just telling all the important points. Then, causality property means if the system's output depends on present and past inputs only, then it is called a causal system. That is, the output is depending only on the present input and the past inputs. Such a system is called a causal system. And what is a causal system? A causal means the output depends on present, past and future inputs. Okay, so such a system is called a causal system. Now this a causal system is generally obtained from the by looking into the region of convergence or ROC. We'll talk about it later. Anyway, you should know that a causal system, because many of the students have heard this term but is not aware of what is actually this causality and what is a causality. So causal means this system is actually influenced by only the present input and the past inputs, not by the future inputs. That is, whatever it is going to come in the future, it is not worried. The system is not worried. But in acausal systems, the system is considering present input, past input and the future inputs. So that is about the causal and acausal systems. Okay, now let us talk about the minimum phase and the non-minimum phase systems. Minimum phase system means, that is, if the system is minimum phase, then the system and its inverse are stable plus causal. Okay, so if the system is minimum phase, then the system and its inverse are stable and also causal. So we have already discussed stability and causality. So if both the conditions are satisfied by its inverse and its system itself, then it is having a minimum phase. Otherwise, it is having a non-minimum phase, we say. Okay, so that's about the minimum phase and non-minimum phase. Now, how to find whether the system is having minimum phase and whether the system is having non-minimum phase? Let us see. Okay, we have not talked about finding the causality and acausality. We'll see about it later while discussing the region of convergence. Okay, so now we are going to see how to figure out from the pole zero plot whether your given system is having minimum phase or non-minimum phase. Okay, this minimum phase property is actually determined with the help of your zeros. So the zeros, as I said, it is denoted by like this. Okay, so if the zeros of the system or in the pole zero plot, if all the zeros are on the left side, that is, if this is a pole zero plot and the zeros are lying on the left side, then the system is having minimum phase. And if the zeros are lying on the positive side or the right hand side or right half of the plane, then it is called a non-minimum phase system. Okay, so in some questions they will be giving the pole zero plot and they will be asking whether the system is minimum phase or non-minimum phase, or in some case they will be giving you a transfer function and they will tell you to draw the pole zero plot and they will tell you to find whether the system is minimum phase or non-minimum phase. So in any of the case, you have to look for the zeros to find whether the system is having minimum phase or non-minimum phase. So if it is having the zeros on the left hand side or the left half of the plane, or the zeros are negative, then it is having minimum phase. And if it is on the right side or the right half of the plane, then it is having non-minimum phase. Simple, right? So that is all about the minimum phase and non-minimum phase system. Okay, now let us talk about the region of convergence. Okay, so we'll do a small example of plotting a pole zero plot and everything. But let us before that discuss about the region of convergence. Okay, so this region of convergence can be defined separately for continuous time systems and discrete time systems, because we know that in continuous time system we are using Laplace transform and in discrete time systems we are using Ising transform in most of the case. So for the case of a continuous time system I am going to talk. So as I said, this continuous time system is using what transform? Laplace transform. So the region of convergence for a continuous time system is defined as the region where the Laplace transform is existing, or it can be expressed with the help of a condition that integral minus infinity to infinity h of t, where h of t is a function given, into e raised to minus st dt is less than infinity. So if, okay, so this is a condition, and in which region of the pole zero plot this condition is satisfied, that region is called the region of convergence, or we can say it is the region where the Laplace, this is the Laplace transform, right? So where the Laplace transform is existing. Now let us see what is the region of convergence for ROC for a discrete time system. So as we said earlier, this discrete time system uses what transform? Is a transform. So this region of convergence for a discrete time system is the region where the is a transform summation converges, okay, or the is a transform exists in general. So what is the equation for finding the is a transform? Sigma for discrete time system. That's why we are using sigma. N is equal to minus infinity to infinity x of n, where x of n is your input. Whatever may be, that is your input. Z raised to minus n. This is the general equation to find the Z transform, right? So it should be, how the condition should be, it should be less than infinity. So where this condition is satisfied, that region is called your region of convergence. Okay, so that is the region of convergence for a system. So it is defined for Laplace transform and for Z transform, that is for continuous time and discrete time systems separately based on the transform conditions. Okay. Now, how can we find out? So we have not discussed about this causality and acausal systems, right? So how can we find out the system is causal or acausal based on the region of convergence? Okay, so let us try to draw a plot. This is a plot. Okay, so j omega and there is a sigma here. Okay, and I am going to draw. So this is a pole and having value of 0.5, and I'm going to draw a circle using this, and there is a unit circle of this pole zero plot having value 1. Okay, now the region of convergence for a causal system is out of this circle. That is, we have drawn a circle with the endmost pole. So okay, so we have drawn a circle, and there is a unit circle here for the pole zero plot. And if the ROC or region of convergence of this system, that is the region where that condition is satisfied. So this is actually a Laplace domain or an S domain. So if the condition is satisfied and that region is extending outside this circle, which is drawn with the outermost pole. So this is a circle which we have drawn with the outermost pole. That is, outermost means it is the endmost pole existing. Other poles are inside the system's area. So if the ROC is extending out of this circle or out of this circle which is drawn with the help of a outermost pole, and this circle will be having a radius of 0.5. Okay. So if this ROC extend outward of this circle, then the system is said to be causal. So this is actually the region of convergence for the system. Then it is called a causal system. Okay, hope this is clear. So we have drawn a circle by keeping the outermost pole as a radius. That is, here the outermost pole is 0.5. We have kept it as radius and we have drawn a circle. And the region of convergence of this system is extending outside from this circle. Then such a system is called causal system. Okay. And what is the opposite? A causal system. So if this region of convergence is existing, that is, it is converging towards this center, that is inside the circle, the region of convergence is present, then it is called a causal system. So for a causal system, if the region of convergence is extending outside or outwards from the circle, for a causal system, it will be like this. So inside the circle, that will be the region of convergence or ROC. So then that system is called a causal system. So if you have given these two circles, if you are being asked to find whether the system is causal or acausal, you should be able to figure out. If the region of convergence is extending outwards, then it is a causal system. If it is towards the circle or inside the circle, the region of convergence is present, then it is called a causal system. Okay. So that is all about the region of convergence and causality and acausality property. Okay, so that is the main things you will be asked to find from the pole zero plot. Okay, so another important thing you have to keep in mind is that the system can be causal and stable. Causal plus stable. Okay, if this region of convergence is also including the unit circle. So the previous figure we have drawn is having a ROC which is extending outerwards of the circle, right? And it also includes the unit circle, means the circle with radius 1. So if such a condition is existing, then it is called a causal plus stable system. That means the system is causal and also stable. So that is another important property. Now I think you are able to figure out whether the system is causal, stable, whether it is having minimum phase or non-minimum phase from the pole zero plot given in the question paper. So these are the very basic things you should know. Okay, now let us try to do a small problem plotting a pole zero plot. Now we have talked about the properties, but we have not discussed how to get the poles, zeros and everything, right? So I'm just randomly writing a transfer function. So this is h of s. H of s is equal to s plus 1 by s plus 2 into s plus 3. This is my transfer function. How to obtain the value of poles and how to obtain the values of zeros. So as I said in the beginning, what is 0? 0 is obtained by equating your numerator to 0. So s plus 1 is equal to 0 and s is equal to minus 1. This is the value of your 0. Now what is the pole? I'm going to find the poles of this transfer function. So there are two factors. So equate both to 0. S plus 2 is equal to 0, then s is equal to minus 2. S plus 3 is equal to 0, then s is equal to minus 3. So s is equal to minus 2 and s is equal to minus 3 are the pole values. And s is equal to minus 1 is the 0 value. Now you can plot the pole 0 plot. Okay, so this is a continuous step system and I am going to plot my pole 0 plot. So there are two axes. There is an imaginary axis. There is a real axis. Okay. So this is actually a very basic thing. Anyway, I am just demonstrating how to do the pole 0 plotting and all. So first I am going to draw my 0. So there is only one value. S is equal to minus 1. So I am going to take this is minus 1. This is my 0. See, I have drawn a small circle for the 0. Now the pole values are minus 2 and minus 3. So I am going to mark induce for minus 2 and minus 3. So this is how you can plot the poles and zeros to the pole 0 plot. Okay. And in reverse, I am going to do in reverse. So now I am having this. How can you draw how can you write the transfer function from this pole 0 plot? So just look for the zeros first. So anyway, from by seeing the figure, it is clear that the transfer function is in which domain? Laplace domain, right? So h of s. First look for the 0. It is present at minus 1. So here s is equal to minus 1, or you can write s plus 1 is equal to 0. So this is your numerator by. What are the denominators? Denominators are actually the factors of your poles. So the pole values are at -3 and -2. So S minus 3 is equal to S is equal to -3, or S plus 3 is equal to 0, and S is equal to -2, then S plus 2 is equal to 0. So the pole values are at -3 and -2. So the factors are S plus 3 and S plus 2. So this is how you have to write the transfer function from the pole zero plot in reverse. Okay, so I hope this concept is very much clear to everyone, and I really hope that you understood what are causality, what is stability, minimum phase, non-minimum phase, region of convergence and everything. At least the basics, because this is very much useful for your semester exams or your class exams, and also when going for the competitive exams. Okay, so please do refer these topics from control system thoroughly, because I've seen all question papers with at least one question from this area. Okay, so if you like this video, please do give it a thumbs up and share this video with maximum of the friends who are preparing for any of the competitive exam related to electronics. And also, if you want more videos, please do subscribe to the channel. Thank you.